Hello, everybody. Welcome back. Today we're going to be looking at Unit 6.5, which is all about the energy of phase changes. So have your calculators out again because you're going to need them, and let's get started. So what you're looking at here is a particle diagram, particulate diagram, showing you, the differences between solids, liquids, and gases, which we've of course talked about before, and just reminding you what all the different phase changes are involved from going from one state to another. And just to remind you that processes like melting and vaporization, those are processes that require energy because we are breaking intermolecular forces. Those are endothermic processes. Things like freezing and condensation, where bonds or intermolecular forces are being formed, energy will be released into the surroundings. Those are exothermic processes. So we keep coming back to that. It takes to break, you're free to form. Okay. And we're going to be looking at sort of the math involved in terms involved with phase changes today. So this diagram may be familiar to you. Maybe you did some heat curve calculations back in Chem 1. And I want to talk about each stage and make sure you guys remember, those of you that have seen it before, what's going on at each stage. And shame on me for not having labeled axes. But what's on the x-axis would likely be energy added or time, something like that. What's really more important is what's on the y-axis, and that is temperature. And this is what's called a heating curve. And I've given you the example of a heating curve for water. So let's say that we take a block of ice directly out of the freezer, and it starts down here at a temperature of negative 20 degrees Celsius. And I put it out on the counter, the kitchen counter. Well, as soon as I take it out of the freezer, its temperature is going to rise, to increase. Okay. And throughout that entire period, it will remain in the solid phase. Once it hits 0, which is for water, that is its melting point, it's going to start to melt, okay? And some of those intermolecular forces are going to start to be broken. Over the course of this stage right here, guys, I want you to notice that the temperature remains constant the entire time. So what's going on during that period? The melting process is taking place. So we're converting that solid block of ice into liquid water. And as soon as I hit this point, that is when all of the solid is now melted. So I am 100% in the liquid phase now at this point. And as soon as that has happened, all of the solid has been converted into liquid, then we can start to raise the temperature of the liquid phase now. Okay, so let's say I take that puddle of water that's on the counter, I put it into a pot, and I put it on the stove. So I'm adding heat. The temperature of the water is rising. It's staying liquid over that entire range until I hit 100 degrees, which again for water is its boiling point. And as soon as I hit that temperature, the vaporization process is going to start. So over the course of that flat plateau there, again, notice the temperature is remaining constant. That is what happens during phase changes. We are going through the vaporization process. That liquid water is being converted into water vapor. And that process will continue until I hit that point when all of the liquid has been converted into the gas phase, and only then can I start to raise the temperature once it is 100% in the gas phase. So it's important that you know which states of matter are occurring at every stage and understanding what is happening at every stage. And it's not always adding heat, heating up, okay? You could look at this same curve, but going in the other direction. What if you were cooling a sample of water vapor down, cooling it down, condensing it, cooling the liquid down, then freezing it, then cooling the solid? You could go the other way, okay? This direction, all of the processes would be exothermic. If I'm moving in this direction, every process would be endothermic. Okay, now let's talk about the math that's involved in these steps, because you're going to have problems where you're going to be given substances at a certain temperature and you're going to be asked to calculate either how much heat has been absorbed or how much heat has been released, depending on what we're doing to it. So if you remember from our last lesson, we learned a formula, Q equals mc delta T. Q is heat, M is mass, C is specific heat capacity, and delta T is the change in temperature. Again, remember guys, that's always got to be final minus initial. Anywhere on this curve where you have a change in temperature, you are permitted to use that formula. The only thing that you need to be a little bit careful about is these specific heat capacities. This would be, if we're doing H2O, for example, I would need to plug in the specific heat capacity for ice. Here, I would need to plug in the specific heat capacity for liquid water. This one would be water in the gas phase, and they have different values. Again, from last class, the only one I would really commit to memory is this one. Specific heat capacity for water is in the liquid form is 4.184. You're going to use that number a lot. But the point is, anywhere you have a delta T, you can use that equation. And it doesn't matter if you're heating up or cooling down. The sign will change, because if you always stick to final minus initial, your heats will either be positive or negative, depending on what the situation is. But what about these phase changes? We don't have a delta T, so we can't use MCAT. So what do we use? Well, on the bottom plateau, where melting or freezing, depending on which direction you're going, we would use this. Heat is equal to the amount of your substance, and I'll explain in a minute why I have this sort of vague term amount, times a quantity called the heat of fusion. Okay, and let me say again, guys, it does not matter if you are going through the melting process or the other direction, the freezing process. You're going to use the same equation. Okay. The heat of fusion value is typically going to be given to you. Now, why do I have this vague term amount? I mean, what is that? Well, guys, it depends. If your heat of fusion is given to you, let's say in joules per gram, those are the units for the heat of fusion, then what should you plug in that space, that placeholder of amount? You should plug in a mass in grams. But sometimes your heats of fusion are given in units like this, joules per mole. And if that's the case, then your amount, what you put in that placeholder, should be a number of moles. Okay, now let's review for a second. Let's say you're going through the melting process and you're going to use this equation. if you are melting something, should your heat value end up positive or negative? Think about it, guys. Melting, what are you doing? You're breaking intermolecular forces. It takes to break, endothermic. If you're melting, your heat value in that step should be positive. Whereas if you're freezing, you're going to use the same numbers, but it's up to you to make sure that you throw a negative sign on there. The process of freezing is exothermic. Okay, now what about at the top plateau where you're either vaporizing or condensing? It's basically the same formula, except instead of heat of fusion, you'd be given a value called the heat of vaporization. Okay, again, if you're boiling, it'll be positive value. If you're condensing, it'll be a negative value. So during phase changes, we can't use that MCAT equation because the temperature remains constant, which essentially means there's no change in kinetic energy. The only energy change is changing the potential. Those are the equations we will use. And remember, guys, it's up to you to know whether to attach a positive sign or a negative sign. If it's an endothermic phase change, it should be positive. If it's an exothermic phase change, you need to put a negative sign on your final answer. Okay, so I've given you a problem here. There's a table of data. It says using the table above to answer the following questions about silver. Okay, now I'm just going to give you one hint on letter A, because I want you to pause the video and try this on your own, but let me give you one suggestion for letter A. Letter A says silver can be purified by melting. How much energy in kilojoules is required to melt 10 grams of silver originally at 950 degrees Celsius? I would highly recommend drawing out that stair-step curve, that heating curve shape. Figure out where on that curve are you beginning, where are you ending, to see how many different calculations are you going to have to do. Okay, but I want you to pause the video, see how you do with this. All right, let's see how you did. Now, as I suggested, I would sketch out that stair-step curve, put a dot where you're beginning and an X where you're ending. Okay, so I'm going to put up my answers, and there's a lot to look at, but I'm going to talk it through. All right, so look on the left-hand side. Okay, you can see my stair-step curve, and I put a dot at 950 degrees. Now, how did I know that the dot would be there? Because the data table, or the information table, told me that the melting point was 961.8. So I knew 950 was below that. So it's in the solid form, and then all we did was melt it. So I went through 2 steps on that stair-step curve, and I labeled the first step as step 1 and the next step is step 2. Now look at the math. Okay, so right here, step 1, since I was on a slant and there was a change in temperature, I used MCAT, the mass, the specific heat capacity, and the change in temperature, final minus initial, and I got a value for Q. So that was the heat required, absorbed, to take the silver from 950 up to 961.8. But that's not where the problem ends. Then I had to actually take it through the process of melting. That's step 2. So here I am, step 2. Okay. On the going through phase changes, you don't use MCAT. We used amount times the heat of fusion. Now, if you look up in that data table, the heat of fusion was given to me in kilojoules per mole. which is why you'll notice under the word amount, I have converted 10 grams into moles by dividing by the molar mass, multiplied times the heat of fusion, and down here at the bottom of the slide, I have 1.04 kilojoules. Now that's not the final answer here. I need to add these heats together, okay? And there's a little bit of a problem though, because this heat is in joules, this heat is in kilojoules, okay? The question said to put the answer in kilojoules. So let's convert this one. We're going to move the decimal point 3 spaces back. 0.0283 kilojoules. And now I can add them together, okay, and round. So if I take these two numbers and I add them together, right, and round to, let's go to 3 significant figures. Here is my final answer. 1.08 kilojoules. Okay, so that's the total amount of energy to not only warm up the solid, but to melt that silver. Okay. Part B said use principles of bonding to explain why the heat of vaporization is much greater than the heat of fusion, which I can see that it is in the chart. It looks like there's a little bit of a typo there. That heat of vaporization should say 250.6. And here's why. All right, think about what's required to melt that silver, heat of fusion. Okay, metals are in a crystalline lattice structure, just like ionic compounds are. And when you go from a solid to a liquid, you are breaking intermolecular forces, but you're not pulling them apart very much. Whereas when you vaporize a liquid, you are completely breaking all of those intermolecular forces. Whereas going from solid to liquid, you're only breaking some of those intermolecular forces. So heat of vaporization, you're breaking all of those intermolecular forces, which is why it requires so much more heat. So this last part, you don't even need a calculator. It says determine the amount of energy required to freeze 1 mole of silver at its melting point. So this time we're starting with 1 mole of liquefied silver, and we want to freeze it. We can still use the heat of fusion, okay? And look at the value, 11.3 kilojoules per mole. How convenient. I'm in moles, okay? My amount is in moles and it's 1. So here's my answer. Ready? The answer is negative 11.3 kilojoules. Okay. The heat of fusion given in that table is the amount of heat required to melt 1 mole of silver. We're going the other way. The heat that will be released when I freeze 1 mole of silver, it's the same number, but now it's negative. And it's up to me to put that negative sign in there. For me to show the graders that I know that the freezing process is an exothermic process. So that wraps up subunit 6.5, which was all about phase changes, but we also brought in some other pieces of just warming a solid or warming a liquid or cooling it down. So knowing what's going on in those heating curves is really important, as well as being able to apply the math to it. So I hope you have learned a little something today, and I look forward to seeing you next time.